Okay, welcome back. The next speaker is Vasudeva Murthy, Vasu for short, my former colleague and colleague in TIFR. He works on various aspects of PDEs, and today he's going to talk about sine-Gordon equation.
Thank you very much, Amit. Also, thanks to Vishal for the invitation. My talk is on sine-Gordon force system. You already had some introduction from Buckingham on this thing. He also mentioned about a large parameter. So just to connect with his talk, there is a large parameter here, but it is implicit and it will come at the end. Basically, I'm on the whole real line R, and then I would like to truncate this to minus L, and so this L will be our large parameter here. What kind of boundary conditions, etc. And I'm not going to be very, my talk is not on doesn't cover very vast area, but it's a specific work. So it started off with a summer student, Isha Saha. She's now doing her MSc in NIT Rourkela. When she came, she was in her BSc third year. And this is Jitin George. He's now a PhD student in Northwestern University. And this is Amiya Jagtap, who's my postdoc. Now, she was worried about the Nepal earthquake in 2015, and so she was wondering if there's a mathematical model for earthquakes. So that was the motivation for this. And this work has appeared in Wave Motion last year. So I'll be specifically talking about this piece of work and connect it with this kind of far-field boundary conditions. So we started looking for a model for faults or cracks in some domain and its propagation. So we hit upon this article by Landoni and Nopov, appeared in 1981 in Geophysical and Astronomical Science. And what they proposed was a wave equation like this with a forcing. And the forcing is something like this. Epsilon into Heaviside function. Heaviside function, as you know, is 1 on the left and 0 on the right. This continues at 0. And then there is this u here, which is the displacement, and epsilon here and 1 minus epsilon. So what he says is that u is a relative displacement of a fault, and c is the velocity of light, and so on. So of course it looks a bit messy, but we will clean it up in the next. So the function looks very much something like this. So there is a drop like this, and then it remains constant. So this is how the forcing of the wave equation looks like. This f of xt is a misnomer here, but actually there is a u sitting here. And it should have been f of xt. So then we also saw that the sine-Gordon has application to earthquakes through this article by Bykov in Journal of Seismology. And he said the sine-Gordon equation is a good model for earthquake study of earthquakes. So that inspired us to just clean up this model and this particular equation. And we wrote down this sort of a non-messy equation, saying there's a sine-Gordon, but with a forcing like this, a constant times the Heaviside function. So in other words, the study of is well motivated to study this equation. So it's not cooked up just for pleasure. So then we decided, why not examine this forced wave equation in the whole domain and with initial conditions like this, and which decays at infinity. So how does this solution look like? So of course you can write down the exact. Suppose f is the constant, then your solution looks something like this. This is the D'Alembert's part, the initial condition, and the forcing integrates it to like this. Now amazingly, when you put in this Heaviside function, these guys remain the same, except this forcing turns out to be like this, x into t minus x. Here you had t square minus t minus x whole square. But here it turns out it is x into t minus x. So that's a bit of a surprise. And if you plot them, they look like this. So this is with a constant a, and this is with the Heaviside. So you see there's some kind of a smoothing. Usually if you had a discontinuity in the initial conditions, that will always propagate. The discontinuity will propagate. Whereas when you have put a discontinuity in the forcing, it seems to somehow smoothen it out. And not only that, this behavior is quite surprising. So this was also done numerically, and we checked that the numerical solution also agrees with this. And the numerical scheme is a straightforward finite difference. You replace it by the second order in time, and then time and space. So if you said that if any point here is xj, then you say that u of xj comma tn is replaced by un at j, and then you replace t square u by dt square by un plus 1 minus un plus un minus 1 at j by delta t square, and then d square u by dx square as un at j plus 1 minus 2 un j plus un j minus 1 by delta x square. So, and then you combine everything to get an explicit scheme like this, and of course your time step will be delta t will be restricted by the Courant-Friedrichs-Lewis condition. And then now we can do the same thing with the sine u term included in the equation. So this is how it looks. So these dotted lines are with the Heaviside forcing, and the continuous lines are with the constant forcing. So if you see the first purple line, this is at t equal to 4 with a forcing of half, constant, without Heaviside. Now you see the corresponding dashed line is with the Heaviside, so it almost behaves like the linear wave equation. And then you move forward at t equal to 8, the constant forcing has a propagation like this, and then with the Heaviside, it's like this, and so on. And you see how if you just concentrate on the dashed line, from here to here, and then here, and then here. On the other hand, the constant one goes like this, and then it seems to oscillate in time. So this is what you see in the case of a Heaviside and a constant forcing in the for the inhomogeneous sine-Gordon. Now, a Chinese guy looked up at this with forcing like this, and he got these plots. The domain is from 2 to minus 18, and then he saw that a wave propagates exactly like this in the other direction. So our numerical solution also agrees with his result as well. So this is just some kind of a validation of the scheme. And now, in order to study this discontinuous forcing, we took these cases of Kink and breather. So Kink is a discontinuity moving, and breather is just like what it says. It's a sort of a pump. It doesn't move in space, but keeps oscillating in time. It's at a fixed location, just like our breathing. So it's called a breather. And these are the two initial conditions for Kink as well as the breather. And now this is where the problem is. Now the domain size in both the cases is minus L to L. And what kind of boundary conditions should you use so as to simulate the infinite domain problem? This is generally an open problem, and there are no hard recipes. It could be physical, and then it could be mathematical, or it could be numerical. So physical means you just get a sort of some kind of an intuition, and then you say that this is how the large problem works. In other words, I'm trying to say what should be L, and then what boundary conditions at L, and plus or minus L. So if you look at aeronautical engineers, they look at flow past aerofoil. Then you have to put it in a, if this is your cross section of your wing, then you have to put it in a domain like this with length minus L to L. So they will do that you take 3 times the span of the wing. Okay. So that is physical. And then if you look at weather prediction, guys, so that is R3 minus S2. So it will be, let's say this is the Earth. You need to put a lid on the top, height. So so you need to cut off, you can't let it to infinity. So for numerical purpose, you need to put a lid there and then prescribe what boundary conditions need to be posed there. So usually this is again based on physics. They will say the water vapor scale height is about 2 kilometers, and so most physical processes are happening within 2 kilometers, and so let's extend it up to some 10 kilometers or 15 kilometers. So the top is, so these are based on physical. Now mathematical would be that you call this problem U of L, and then plus whatever boundary conditions you pose. And this should go to U as L goes to infinity. If you can prove a result like this with the boundary condition which you have posed, then that would be mathematical. Numerical would be you keep extending your domain, L plus delta L, and then L plus 2 delta L, such that two solutions do not differ. So that would be numerical. Now in the lack of any of these things, we just by in an ad hoc manner, we just chose the flux boundary condition at plus or minus L is 0, and or the reflective boundary conditions, non-reflective. It says that here you put ut plus ux is 0, and here you put ut minus ux is 0. Yeah. So here's what the solution looks like. So what we did was we kept gradually increasing 0 to 0.03, and then from a sharp behavior it gets smoothened up. And then we know that the soliton propagation, as Buckingham also mentioned, it was physically observed in Edinburgh. And the soliton structure gets destroyed as you keep increasing the A. So here's, and then it starts the small kink appearing there also. This is the XT plot, by the way. Sorry. And so what's the figures are not important, but what conclusion is that without any forcing, it exhibits soliton-like behavior. The soliton just moves without losing its shape or size, without any decay. There's a nice balance between the dispersion or dissipation and the nonlinearity. That's exactly what Buckingham was also mentioning, that if you had, see, either whenever your initial condition is something like this, it either decays like this, or it splits into smaller waves, or the wave, it breaks up like this. But then this is for ut plus ux equal to 0. But if you add an epsilon u either x or u triple x, then as in the previous Buckingham showed, there will be oscillations, and if there will be a nice, if there is a balance, exact balance between this nonlinearity and dispersion, then nothing of this sort happens, and the wave just keeps moving without either dissipation or dispersion. So that behavior is seen for A equal to 0. And this moves with a constant velocity and reflects back from the right boundary. Okay. Whether this is correct or not, we don't know. The infinite dimension, infinite domain behavior or not, is not clear. So similarly, for small a, it still exhibits, but there's a slight change in the velocity. And as you keep increasing, it increases the curvature of the trajectory. That means there's some distortion in the shape. And when for higher values, it starts moving towards the left. And again, for even higher values, the solution is completely destroyed. This changes the shape of the wave due to, and oscillations are there even before reflecting from the left boundary. And there is a critical A at which the soliton behavior is completely lost. And now with non-reflecting boundary conditions. So with it's exactly similar, and here's a plot. What is C? C is in the initial conditions. So the C sitting there is in the, the C is sitting here. So when you keep changing C and then examine how the A critical value is, so we keep increasing the size of the domain from -20 to -160, and then it sort of, whether this is in, why not go further, but then computational resources are limited, so we can't go beyond this kind of value. Okay, now for breadth with non-reflecting boundary conditions. At A equal to 0, it keeps, it goes up, goes down, goes up and goes down at the same fixed location. Okay. And this is how. And now if you increase A, that breadth profile, it gets destroyed completely. At 0.0076, it's completely lost. From 3 to 2, and then as you keep increasing from 0.1 to 0.5 and 0.05 and 0.07 and so on. And then for small a, there is little change compared with 0. And then as the frequency keeps changing, and as you keep increasing, and for this value, the solution is completely destroyed. You must remember that when there is no forcing, the sine-Gordon equation is completely integrable, and then we have many invariants. So whether with forcing, it is known that it is no more integrable. So so the critical value is around this, for which this Breather solution is completely destroyed, but with the flux boundary. So then again, we looked at the variation of A critical with C, and then it goes on increasing because we can't hit 1 up to 0.9. So the A critical increases with C. And then one interesting feature observed was by increasing the value of C, the temporal frequency of oscillation increases. But at the same time, if A increases, these oscillations shift towards the left boundary. So this is what happens with 0.8 and A equal to 0, and 0.25. This is for 0 and this is for 0.2. So the conclusion is that the numerical solution of this has been investigated for this discontinuous Heaviside function, and this can simulate some dynamical stress drop in one-dimensional crack propagation problem, etc. And this has been solved using no flux as well as non-reflecting boundary. And in the Kink test case, for small amplitude of A, the solution still exhibits soliton-like behavior, but changes the direction of as well as velocity. So for higher values of A, it completely destroys the soliton behavior. So this is a numerical study for these kind of particular boundary conditions. So of course, it's nowhere near being satisfactory. So what is the issues? So what we need to do is we need to, as I already mentioned to you, what has happened for the heat equation. Let's see what for other PDEs, what kind of solutions have been found for infinite domain problem. Is it really a big issue? The question is, I want to study PDEs posed on the entire domain. Now, numerically, we cannot handle the entire domain simply because we are not inverting infinite linear systems. Correct? We are always inverting only finite linear systems. So, how to simulate infinite domain problem using finite domain techniques? So, the simplest PDE you can think of is the heat equation. And let's say we don't want to do infinities, we'll just say one-sided infinity for x positive. And this initial condition is vanishing at. So again, the same issue. What kind of boundary condition should you choose at L so that it converges to U as L goes to infinity? It turns out that it is this boundary condition that you have to choose. This has been normalized, but suppose instead of 1 you had L here. Okay. So the boundary condition that you have to use is Ux plus G with the memory term. So G is J of Ut, where this is convolution with square root function, 1 over square root. So in other words, G should be 0, of course. If Ux at L of t plus Gu at L of t is 0. and this is the initial condition, and f. And this is x in 0 to n. It has been normalized. So only if you use this boundary condition, you are sure that this will be satisfied. So in other words, you use whatever L you choose, doesn't matter. You need to impose that condition, and then it can be rigorously shown that as L goes to infinity, that UL converges to the infinite domain. And we did a finite difference analysis on this using this non-local boundary condition, and there is some surprise. So the only surprise, these things are the standard, whatever I mentioned here. Everything is same, except that we discretize this integral also here. This integral has been discretized, and it's written in this fashion. So the discrete problem is the discrete heat equation here with the boundary condition at the left, and then initial condition, and at the right, this integral condition is there. And this is the Courant CFL number. K is the time step, and H is the special step. So you remember in our classical textbooks on numerical methods for PDE, the convergence says that if lambda is less than or equal to half, then you have a discrete solution converging to the exact solution, numerical solution. The numerical solution converging to the exact solution. But because of this kind of boundary condition, you also need that lambda should be bigger than or equal to lambda naught, and that should be bounded below by 1 over pi. In that case, you can show that not only this is stable, also the solution actually converges to. So in other words, the infinite domain effect is seen in this condition. Usually you don't need this, lambda bigger than this, but you do need this. So that is the reflection of the infinite domain. Now you may say that, does it really matter? So usually this particular result, that this condition was discovered only in 2002. The original problem, as we say, the necessity is mother of invention. So what happens is that the actual problem people were trying to look was the semi-linear heat equation. Ut equal to uxx plus u into 1 minus u, x in the whole space, and with this initial condition, at left it is 1 and at right it is 0. And then we need to compute traveling wave solutions, just like soliton kind of. So if you were to look at the initial condition, which is yeah. So what I'm plotting here is x, and this is u. So if your initial condition is 0, and then it is 1 here. So this is our u0 of x. So for very small time t positive, what will happen is it'll get smoothened because the heat equation is smoothing behavior. And then what happens for subsequent times, it will start moving like this. And then it will occupy the entire, the whole thing becomes 1. And this is propagating with the speed c. And so we need to look at solutions which are like this, p of x minus ct, and the question is, what is the c here? And if you want to do this numerically, of course, obviously you will have to cut it off at L, and then another L here, and we would have put the usual boundary condition here as 1, and then u at L of t is 0 here, right? This would have been the naive boundary condition that we would have tried. So the question is whether it really simulates the infinite domain. And it turns out that there is a theoretical result, which is that for all positive initial conditions which decay exponentially as x goes to infinity, that will evolve into a unique traveling wave with speed bigger than or equal to 2. And what does that c depend on? It depends on the decay rate. So if your initial condition is decaying at the rate of beta exponentially, so your speed will be 1 plus beta square by beta if beta is less than or equal to 1, and then it is 2 if it is larger than or equal to 1. So this is a theoretical result proved for the entire domain. Now, if you want to capture it numerically and you do this kind of boundary condition, it turns out that you always get c equal to 2 for all beta, whatever the initial condition. So that you remember even previously, even for the simple heat equation, you had to have lambda bigger than lambda naught if you want to capture the far field. So obviously this is not a surprise, but nevertheless this was done in '86 actually. So the nonlinear problem was first tackled, and boundary condition was derived for that, and it turned out that if one did not know this theoretical result, then one would assume that this is c, the speed is always 2, and then have tried proving a result saying that traveling waves are always propagating with speed 2. Since the theoretical result came first, it turned out that it was better. So what is it? So in '86, the boundary condition which was proposed is a distant and a messy cousin of whatever I wrote in the previous case. It's more messier than this guy. So you see here ux plus g it's clean, whereas this one is quite messy with so many functions sitting around here. So here also you have square root of t minus s, ux at L of s and ul of t, plus all kinds of complementary error functions. Error function, 0 to x, e to the minus t squared dt, and ERFC would be 1 minus ERF. So using this boundary condition, they were able to show that you could actually get speed more than 2. They were able to get up to speed c equal to 4. So what is a strategy now in use here was you truncate the domain like this, and then in this region you solve the linear problem. You solve the linear problem and then you get the value, whatever value you feel like, and then you match it with this. Use that as your boundary condition. So that was the technique used there. So nothing, as I said, you linearize outside the domain and you match it to the interior. And of course you hope or prove that the resulting initial boundary value problem is well fixed. Okay. Now we need to do the same for the sine-Gordon. That gets, and use that boundary condition. And somebody did do that, but it's so complicated. That's what I will do. So this is what this guy did in 2007. And he looked at this sine-Gordon, the entire real axis. And of course, this was not with forcing. So after this, we need to extend it to our forcing case. So what he says was, you need to have the Neumann condition at A is related to the both Dirichlet and Neumann condition. It will be a functional equation between the Neumann value, the derivative value, and the functional value. Similarly at B, exactly similar to what we had in the heat equation. But only thing is, this is much more complex. So what kind of an operator is this K? So K looks something like this. Suppose G0 and G1 are arbitrary functions. Then the relation is expressed by 0 to t, G0 dot, and Z is a kernel given by this, which is related to the Bessel's function. And also all these are known functions, except that you can't integrate exactly. So this also says something about the integrability. So now, and the relation between G1 is given in this fashion. And what is M1 and M2? All these things we know. G0 is, as you can see here, it is the Dirichlet and the Neumann map. And here, Z is known, and the only thing is we need to find what is M1 and M2. Now here's a plot of this function Z of t. Remember, Z of t is well known, except that you can't get a closed form expression for this. You have to do it numerically. So it has been done numerically, and here's the plot for t up to 16, and it varies from -1.5 to around 0.5, and it looks something like this. And now the relation between M1 is the following. L1 is known, it's in terms of the boundary data. M1 is sine of this, and L2 is, this, and so on. So there is a, in other words, these M1 and M2s are obtained from, the M1 and M2 given here is obtained from these complicated expressions. Not complicated, messier. So the cure is worse than the disease. So, and so everything is known there. So only thing is Now that is based on this paper of focus, which appeared in 2005. CPA. He gave a generalized Dirichlet-to-Neumann map. Take any point, if U solves the sine-Gordon or any nonlinear thing, take any point, what is the relation between the function and its derivative? So he gave a general for nonlinear evolution. So now our question is, can we have simpler boundary conditions? And of course, with these simpler boundary conditions, can we hope that the solution converges to the infinite domain problem? So for example, this is a boundary condition which has been recently used at x equal to 0. With this kind of boundary condition, the far field boundary condition also gets easier. Okay. So then, and this is, for instance, this particular paper has been not well studied, I think, except for, say, for a few, who has given a general recipe for boundary conditions for integral equations. How you should get that. It's a Russian journal. And we need to take these boundary conditions for the specific case of simpler boundary conditions, and then try to show that the finite domain problem actually converges to the infinite domain. Now this is what is a program, much bigger program and complicated, and that is what I've been looking at. So I think that's the end of my talk. So in other words, this boundary condition is really extremely complicated to implement. It's just, as you saw, even for the simple heat equation, it was a big pain to implement this because it has a memory. So you have to store all the values. So when you discretize, what happens is, this see here, this GM will have all the values stored at the boundary. 0 to t you have. Usually this is a local, non-local condition. So when you have a non-local in time, you need to store the value at 1 for a long time. And that is what makes it even for such a simple case. And the fact that it is important is given by this problem, namely for this wave equation, nonlinear population dynamics or nonlinear semi-linear heat equation, where if you want to capture the wave phenomenon, then you will get the wrong kind of wave speeds if you do not implement the boundary condition correctly. So in other words, we can't sort of assure ourselves that the solution which you are getting using finite domain actually simulates the infinite domain. So especially in problems like tsunami and earthquake, etc., then you need to know what's the far field boundary conditions. And these far field boundary conditions appear in many places, and especially in weather prediction, flow past aerofoil, etc., and all that. Now, in the case of integrable systems, there is a well-oiled theory by this person, but it's still, he has made a proposal on what kind of boundary conditions you need to use for integrable equations using Lax pair and inverse scattering transform. But again, we need to, by using that, are we assured of this criteria? That is a big program that needs to be. So I think I'll stop. I'm sorry, it's like this. Sorry, here it is. Okay. So the question you are asking is, there will be x minus ct here, sitting here, and then you are asking under what conditions the solution will converge to this solution. Yeah, this is a kink. These are the initial conditions for kink. These are the initial conditions for breather. Okay. So in this particular case, you are asking under what conditions it will, I don't know, maybe Buckingham will answer. Basically, you are asking interface from oscillatory to decay, right? So, yeah. Oscillatory in space to oscillatory in time.
I have a question.
Yeah.
So, let me see if I understood this right. So the goal is to solve a whole line problem using a finite interval, and it to me, it seems like the strategy here is to actually consider the whole line as two regions, and then treat that as almost like an interface, at an artificially introduced interface at one point. And so then is that precisely how you derive what the boundary condition ought to be? Let's say that I started off with zero initial data.
In the case of dissipative problems, like the semilinear heat equation.
Yeah.
But in the case of these wave propagation problems, it's not clear.
I see.
From oscillatory to decay or oscillatory, which will happen. You ask the atmospheric guys, what do you do on the top of it? They say we put a sponge.
Right.
So,
right.
Yeah, that's the kind of answer you'll get. So you want the waves to be absorbed or waves to decay at that point, so as to capture the entire domain problem. It's not clear.
Right. I guess I had a more sort of preliminary question, which was just the strategy to reduce a whole line problem to a finite interval problem is put an artificial boundary and then try to somehow analytically solve the infinite line part, map it to some boundary condition at the artificial interface, and then just deal with the finite interval. Is that the strategy?
Yeah, that strategy works for heat, and it is just a time-dependent integral you get. But in the case of sine-Gordon, it is quite complicated.
So the boundary condition you showed, isn't that coming from a similar process itself? Like that's how you get these maps from one boundary datum to the other boundary datum?
Yeah, but in this case, it's slightly more involved, I think.
Right. And these integrals are also oscillatory integrals, right?
Yes, yeah. Okay. So it's based on the work of this. This boundary condition is just an application of this technique by this Chinese man on the sine-Gordon without forcing. Now we wanted to include the forcing also. So with forcing, how do you actually get into it? In other words, integrable boundary conditions. Of course, the same questions, I don't know if it has been asked for the matrix case. Suppose you had a map A from L2 to L2. And then you want to invert this guy, AX equal to P. And then what you do is you truncate it, correct? You truncate AN of XN equal to Pn. And then you hope that Xn will converge to X as n goes to infinity. Now this guy is in Rn. Right? So now we are asking questions like, suppose A is orthonormal or orthogonal with specific properties of A, unitary, etc. Then your truncation should also be unitary or not. All kinds of questions are there which you can ask. So it's exactly very simple. Only thing is, this is a pain to implement. If only we had something like this, this looks more cute and simpler. So, but the exact solution itself is a bit surprise, correct? The wave equation, and although we know how to write it down, that behavior can be like this. Even for linear was a real surprise. And here there is no numerics. Here is purely explicit. So this is with constant forcing, and this is with the Heaviside forcing. And then the solutions are given explicitly. You just forget about this. It changes from this to